In this lecture, we are going to actually solve linear systems using our elementary row operations and a method called Gauss-Jordan elimination or Gauss-Jordan method. So I will illustrate step by step how we do it. So let's try to solve this linear system. So that's how the question comes. So I have this system here. First step, I need to rewrite this in augmented matrix form. So rewrite the system in augmented matrix form. And this will be the first step for all of your procedures. So let's form augmented matrix. So first equation in front of x1 is 1, then 0 times x2, then minus 2 times x3, slash, and then 2 on the other side. Okay, cool. Second equation, I have 1 in front of x1, and then minus 1 in front of x2, 5 in front of x3, and 1 on the other side. Last equation, minus 1 in front of x1, 0 in front of x2, and 2 in front of x3, and on the other side is 0. So this is my augmented matrix form. Beautiful. So what do I do now? I will use elementary row operations. You remember that we have 3 of them. We have swap. We can swap 2 rows and it will not change the solution set. We can multiply 1 row of our choice by any number different from 0. That will not change the solution set. And we can add 2 rows together with a multiplication on one of them. And that will also not change our solution set. So we have those 3 operations. We choose the one we like and we go ahead and try to solve all this. So we can spin those elementary operations till tomorrow, but we need to be smart and wise. And that's where the Gauss-Jordan procedure or the method is important. The goal is to put in the left top corner a number different from 0, ideally 1, and you will see why. So in this case, we are blessed, we have 1. Beautiful. So then what we do, we try to eliminate the other 2 components below. So we need to produce zeros below. So this will be called the leading entry, and then these need to be 0 somehow. So how do we produce zeros? Why? Well, if I produce using my elementary row operations zeros here, I know already that the solution set for this system and the new system will be the same solutions. But if I have 0 here, you understand that there is no x1 in the second equation anymore. Ah, that's beautiful. And then there is no x1 in the third equation anymore. That's beautiful too. So the idea is actually, by producing these zeros below leading entries, is to eliminate, let's say, x1 from all the equations after the first equation. So we kill x1 from second equation and third. That's the goal. And then we will do something similar later on for other variables. So after we are done, then for the x2 we want to kill it in all equations starting from the third equation below. So let's see how this works. So I use my elementary row operations and Gauss-Jordan method to solve the linear system. First step, from the system I write the augmented matrix. So let's now see how we need to apply this in a smart way so that actually we produce zeros below the leading entry. So my 1 is the leading entry, so I'll put it in red for fun. So this is your leading entry. Also in your book it's called pivot, and the column containing leading entry is called pivot column, just another name to remember. If you don't, it's not a big deal. Just leading entry and then zeros below. That's the idea. Okay, so I need to introduce 0 here. So how do I do that? Using elementary row operations. Well, I need to replace row 2 by row 2 minus row 1. And that's the beauty when you have 1 in the upper corner. You can easily do the multiplications here that you need. In this case, it's just subtracting, it's fine. But later on, if I have 7 here, instead of 1, then to kill the 7, I would say, well, you need to replace row 2 by row 2 minus 7 times row 1. So, beautiful. So this is the first operation I need to do. So, first row doesn't change. So I just copy carefully so I don't make any mistakes. I'm not copying row 3 yet, you will see why. I can do 2 operations on different rows at the same time. That's beautiful. So now I need to have row 2 replaced by row 2 minus row 1. So 1 minus 1, 0, that's why I did it. And now we start the fight. I have minus 1, minus 0 is still minus 1. And then 5 minus 2, so 5 plus 2 is 7. And then I have 1 minus 2, which is minus 1. So again, 1 minus 1, 0, minus 1 minus 0 is minus 1. 5 minus 2, so 5 plus 2, 7. 1 minus 2, minus 1. Good, so I introduced 0 in the second column, in the second row. So now I want to introduce 0 instead of minus 1. So what I'm doing, I'm replacing row 3 by row 3 plus row 1. Once I have my 0 below the leading entry, I don't touch it. It's beautiful. So now I want to introduce 0 here. Perfect, so I add them. I figured out that that's going to work. 0 plus 0, 0. And 2 plus minus 2 is 0. And then 0 plus 2 is 2. Gorgeous. But wait a minute. What just happened? I need to add these two guys to kill this guy. So 1 plus 1 minus 1, 0. 0 plus 0, 0. 2 minus 2, 0. Okay, no error. 0 plus 2, 2. Weird. What's going on here? There's something going on here. This equation says, remember, I used elementary row operations. So this system, original system, and this system, they have the same solution set. If there's nobody in the set here, so there's no solution, then there's no solution for this guy. Okay? If there's only one solution for this system, then there's one solution for this system, the same one. If this system has infinitely many solutions, then this system also has infinitely many solutions, the same solutions. But wait a minute, what happens here? I have 0 times x1, which is 0, plus 0 times x2, which is 0, plus 0 times x3, which is 0, so 0 plus 0 plus 0 is 0, equal to 2. So it tells me that 0 is equal to 2. Like, no way. No way. So this is a contradiction in the system. Because this says 0 times x1 plus 0 times x2 plus 0 times x3, which is equal to 0, but this is different from 2. It is telling me that it's 2, but it's not 2, it's 0. Hello? So there is a contradiction in my system. It's clear from this equation. I have a row of zeros in coefficient matrix, slash, and then something that is different from 0. Well, Sorry, but this is not true. So if it's not true, there's a contradiction. If there's a contradiction, this system doesn't have a solution. If this system doesn't have a solution, then the original system doesn't have a solution. It's clear from here. There's a contradiction in the system. And the system doesn't have a solution. You cannot find x1, x2, x3 such that this is true. There's no way. So if this system doesn't have a solution, well, this system has the same solution set, which has nobody inside. So this system doesn't have a solution. So that's what I write. But looking here, it's not obvious to figure out that this system doesn't have a solution. But when I apply elementary row operations with the goal to produce zeros beneath the leading entry, well, miracle happens, and then I can see clearly what's going on in the system. Isn't this beautiful? So by applying elementary row operations and Gauss-Jordan method technically says put zeros below leading entries. And we will see it says also something else. Leading entries need to be 1, and then put zeros above them also. We will see that in the next example. So this system and this system have the same solution set, but this guy has a contradiction, so there is no solution for this. I cannot find x1 and x2, x3 such that 0 is equal to 2. There's no way. Okay, that's what it means. Oh, okay. Beautiful. So that's one example where we don't have a solution. What do we do? Nothing, it's over. This system doesn't have a solution, we are done. Cannot solve it. So when somebody says, oh, every problem has a solution, well, this one doesn't. Okay? So those who say that never came to linear algebra course. Okay, problem is over. Let's take another one, because this one doesn't have a solution. Fine. So example 2. Instead of just saying solve, I'll say now, for fun, just to change vocabulary, use elementary row operations and Gauss-Jordan method to solve the following system. These are just different ways of saying the same thing. Because elementary row operations and Gauss-Jordan method are the only allowed ways to solve linear systems in this course. So I say now Gauss-Jordan process, Gauss-Jordan method, just to vary the vocabulary. Okay, so what's my linear system? So I have 2 times x1 minus 2 times x3 equal to 2, and then x1 minus x2 plus 5 x3 equal to 1, and then minus x1 plus 2 x3 equal to 0. Well, if you compare this system with the previous one, the only difference is the coefficient here. Here coefficient is 2, in the previous one it was 1. Everything else is the same. Okay. So we write the system in augmented matrix form. 2, 0, minus 2, slash 2. Second row is 1, minus 1, 5, 1. And the last row is minus 1, 0, 2, 0. Okay, cool. So now we are going to apply elementary row operations to produce zeros beneath leading entries. Technically 2 is a leading entry, so we should keep it as it is. But we are not strict to that point. We can swap these two rows, row 1 and row 2, so we have 1 in the corner. That would be cute. Okay, obviously you have 2 minus 2, 2. You can divide first row by 1 also. So those are two options. You can swap row 1 and row 2 because you like to have in the left corner 1. It's very useful for the replacement operation. In this case, since you have 2 minus 2 and 2, well, everything is divisible by 2, so you can simplify a little bit. Your choice what you do. Let's say I had 2 minus 2 and 7, while dividing by 2 would not be cute because I would have 7 over 2, and I don't like fractions. There's nothing wrong with doing that. That's perfectly legal, perfectly fine, but I don't like working with fractions. Okay? So I try to avoid fractions as much as I can. So that's why in that situation, if I had 7 here, I would swap these two rows. That would be my first thing to do, because I don't like fractions. But if you like fractions, it's fine. Up to you. So let's write apply the elementary row operations and Gauss Jordan. Okay, how do I do that? Well, I have two options. Both of them are viable. You choose the one you like. Well, I will divide first row by 2 because that one we don't use it often. So let's see how that looks like. So I'll just clean to have some space. So my choice is to say I replace row 1 by 1 over 2 times row 1. If somebody wants to swap row 1 and row 2, perfectly fine, no problem at all. Your choice. And then what I get from there is 1, 0, minus 1, 1, and the other two stay the same. And you notice that since I'm working now on row 1, until I finish, I cannot use the row 1 until the next step. So I need to write clean and proper my entire matrix. So now this matrix, reflects this operation. So now I want to get rid of this guy and this guy. So what do I do? To introduce 0 in row 2, I say row 2 minus row 1. So that was, so first row stays the same. A little bit too big. So 1 minus 1, 0, minus 1, minus 0, minus 1. 5 minus minus 1 is 6. And 1 minus 1 is 0. Good. Now I want to introduce 0 here, so I work on row 3. So row 3 is replaced by row 3 plus row 1. So that's why I like to have 1 in the corner. It's very simple to do computations. So this is 0, 0, 0, 0. 2 minus 1 is 1. And then 0 plus 1 is 1. You see? Things changed. In the previous example, at this stage I had a problem, now I don't have a problem. So this is called leading entry, and I have zeros below. This is also leading entry, I have zeros below. Okay? And then I have this also leading entry. Okay, nothing below, fine. So you see what happened here. In equation 2, x1 is gone. In equation 3, 1 is gone and x2 is gone. So I know what is the value of x3. 1 times x3 is equal to 1. So x3 is 1. I know it already. But I'm not a baby. I want to continue working with Gauss-Jordan. So applying elementary operations, you can spin that till tomorrow morning. But you need to have a goal in mind. And the Gauss-Jordan procedure gives a goal. What's the goal? Is to have zeros below leading entries. Cool, we have that. And then we want to have zeros above leading entries. Why? Well, we eliminate more variables. So let's kill this guy and this guy. So now my goal is to introduce 0 here and here. So I replace row 2 by row 2 minus 6 times row 3. Very nice. Okay? So 0, 0, 1, slash 1. So row 2 is replaced by row 2 minus 6 times row 3. Okay, 0, 0. This one minus 1. So 6 minus 6, 0. Beautiful. That was the goal. And then I have 2 minus 6 times 1. So 0. 0 minus 6 times 1. So 0 minus 6. Minus 6. Nice. Now I would like to kill this guy too. Eliminate x3. So what I did, I eliminated x3 from second equation. It would be fun to eliminate x3 from the first equation. So row 1 is replaced by row 1. I just need to add them. Plus row 3. So row 1 plus row 3. Okay. Theta 0. Minus 1 plus 1, 0. Beautiful. 1 plus 1, 2. Gorgeous. Very nice. So now, what do I do? Well, I have minus 1 here and minus 6, so I'm going to multiply the row 2 by minus 1. So I'm going to do it here. Okay, let's do it here. Why? Well, that's part of the Gauss-Jordan process. We want to have our leading entry 1 below everything 0. Then leading entry 1 below everything 0. Then leading entry 1 below everything 0. Okay, there's nothing. Then my leading entry needs to have zeros above also. Done. My leading entry needs to be 1 and has 0 above. The only thing is left, I need to replace row 2 by minus 1 times row 2. And then I'm going to be a happy man. So row 1 stays the same. 1, 0, 0. 2, and then 0, 1, 0, 6, then 0, 0, 1, 1. Very nice. So what's beautiful about this matrix, this part here is called identity matrix 3 by 3. So from here, I see that x1 is equal to 2, x2 is equal to 6, x3 is equal to 1. Right? Beautiful. So the solution is, for my x1, x2, x3, I had 3 variables. So x1 is equal to 2, x2 is equal to 6, and x3 is equal to 1. Ba-bam. Oh, but this is a unique solution. There's no parameters, nothing. So this is unique solution of the original system. Of the system from the beginning, this one. Okay, so this system has one unique solution, which is 2, 6, minus 1. So x1 is 2, x2 is 6, and x3 is 1. So now we are happy, everything is done. The big question is, have we made any errors? How can we know? Well, one of the things is we can try to plug this solution into the system and see if it satisfies every equation. So if I put 2, 6, and 1 in here, so minus 2 plus 0 plus 2 is 0. Ah, cool. Minus 2 plus 2 is 0. Beautiful. Let's see this one. 2 minus 6 is minus 4 plus 5 is 1. Oh, beautiful. Let's see this one. Ah, if this one doesn't work, we are dead. So I have 2 times 2, that's 4, minus 2, because x3 is 1. So 4 minus 2 is 2. Wow, yes. So this is the unique solution of this system. Wow. Beautiful. And you saw compared to the previous system, the only difference was one number. Here is 2, and the previous one was 1. And the other one didn't have any solution. This one has unique solution 261. Isn't this beautiful? Which means you cannot just judge your system just by looking at it. You need to work. And again, the reason why I have 1, 1, 1, that's the part of Gauss-Jordan process. You want to have your leading entry, 1, and zeros below. And then leading entry, 1, and zeros below. And leading entry 1 and zeros below. Ah, nothing. But at the same time, your leading entries need to be 1, and entries above the leading entries need to be 0. Entries above leading entry need to be 0. So that way, I have what is called a reduced Echelon form. We will see that later on. And when I have that, that's when I stop the computation process from Gauss-Jordan. So Gauss-Jordan actually tells us what's the goal and how to use elementary row operations to solve the system, and when do we need to stop, because we can spin those elementary row operations for 7 days. But we need to be smart about it, and Gauss-Jordan process tells us how to be smart about it. What's the goal? Produce zeros below leading entries, make sure that your leading entries are 1, and then produce zeros above leading entries. Once you do that, you will end up with something called reduced Echelon form, and that's when you stop. From this, I write the final system, and then I get the solutions. Okay, cool. So let's see another one. So example 3. Again, use elementary row operations and Gauss-Jordan elimination to solve the linear system. Well, I erased that. Okay, fine. Doesn't matter. So I'll just change the system to see what happens. And it is important that you practice this. So the linear system. So let me pick a linear system. Let's work with something cute. So x1 plus 2 x2 and then minus x3 equal to 3, and 2x1 plus 3x2 plus x3 equal to 1. So this system has 2 equations and 3 unknowns. Oh yeah. So if these 2 equations are in contradiction, then the system doesn't have a solution. If these 2 equations are not in contradiction, which means they are consistent, then we will have infinitely many solutions, because at least one of the variables will be free, and you will see how that works. Miracle, miracle. So again, we write the system in augmented matrix form. I'm writing this now. You don't need to write it. You will just do it. Okay? I'm writing because we are kind of learning the stuff. So for the first equation, coefficients are 1, 2, minus 1 slash 3. And the second equation, 2, 3, 1, 1. Okay, cool. So this is my augmented matrix. Now use elementary row operations to produce 0 below. Just a question, what would happen if by some miracle I wrote these two equations but in opposite order? Well, you would swap, because that would be a smart thing to do. You want to have one as a leading entry always. That's the best leading entry in the universe. Okay, so I want to produce 0 here using my elementary row operation, and my Gauss-Jordan tells me produce 0. So row 2 needs to be replaced by row 2 minus 2 times row 1. That's why 1 is useful. It's easy to work with. So first row doesn't change, so I copy it carefully so I don't make any mistakes. Now 2 minus 2 times 1, so 2 minus 2 is 0, that's why I did it. And then 3 minus 2 times 2, so 2 times 2 is 4. So 3 minus 4 is minus 1. And then I have 1 minus 2 times minus 1. Okay, this one is complicated. Ooh. So I have 1 minus 2 times minus 1, which is 2. So it's 1 plus 2, which is 3. Okay, you're not sure? No problem. I have 1 minus 2 times minus 1. So 1 minus 2 equal 1 plus 2. Yay! I know how to compute. Or I use my calculator because I never learned how to compute. Your choice. So row 2, now I'm at the end. 1 minus 6 is minus 5. Wow. Beautiful. So I have my leading entry 1, and below I have all the zeros. Cool. The next leading one is minus 1. Below, there's nothing. Beautiful. But I need to have 1. So I'm gonna multiply row 2 replaced by minus 1 times row 2. Okay? I'm gonna try to squeeze it here, because that's not a big operation in life. Just change signs. Okay, cool. So now Gauss-Jordan tells me use your elementary row operations to produce 0 above your leading entry. So I have my leading entry here, I need to produce 0. How do I do that? Well, replace row 1 by row 1 minus 2 times row 2. Isn't it beautiful when our leading entries are 1? That's why we do it. People were smart to come up with this. So you have your elementary row operations that make sure that the solution sets remain the same through the operations, which means this system, okay, this system has the same solution set as this system, which has the same solution set as this system, which has the same solution set as the new system I'm going to write. So all that is beautiful. All that happens because we are using elementary row operations. Gauss-Jordan tells us how to use them smartly. So now row 1 replaced by row 1 minus 2 times row 2. So row 1 replaced by row 1 minus 2 times row 2. So 2 times 0 is still 0. And then 2 minus 2 is 0. And then minus 1, oh, again. Minus 1, and then I have minus 2 times minus 3. Minus 2 times minus 3 is 6. So I have minus 1 plus 6. That's fine. Or whatever my calculator says. Row 1, 3. Minus 2 times row 2. So 2 times 5 is 10. So 3 minus 10 is minus 7. This is reduced echelon form. How do I know? Well, we will learn that later. I have my leading entry, 1, and 0 is below. Yes. Have my leading entry in the row 2, and 0 is below, well, because there's nothing is finished, and 0 is above. Yes, done. So this is my reduced echelon form. Yes, sir, I'm done. So now from here, I write my equation. So what I'm doing now is rewriting the augmented matrix form in terms of the system. So here, this says x1 plus 5, or maybe I will write it so you know what I'm doing. Reduced. echelon form. For now you don't know what it is, you will learn and you will hate it. Well, actually you will love it because it helps you solve the system. Rewrite the augmented matrix form as a linear system. So that's what we are going to do systematically. What does that mean? Well, first equation says it's x1 plus 0 times x2 plus 5 times x3 is equal to minus 7. And the second equation says x2 minus 3 times x3 is equal to 5. And you go, okay. Well, there's something else that you can see. x1 will be called main variable because first column has the leading entry. This is pivot column in your book. Second column has the leading entry, also called pivot, also called pivot column. So x1 and x2, they are main variables. And x3 is free. That's what I read from here. Since it's free, well, we will have infinitely many solutions. Beautiful. So I will rewrite this. So x1 is equal to minus 7 minus 5x3. Gorgeous. And x2 is equal to 5 plus 3x3. These are the expressions for x1 and x2. Beautiful. And x3 is free variable. Free variable. Which means x3 can take any real value. But x2, well, it needs to follow this formula. And x1 needs to follow this formula. So x3 is totally free, x2 needs to be computed like this, and x1 must be computed like this. So let me write that. What is the solution? We are almost done. One more step, just to write the solution. So the solution is exactly the same expression for all of the intermediary linear systems. Original linear system and the others, they have the same solution set. That's the beauty of elementary operations. Hence, okay, so let's not write this, let's write it in a more careful way. A general, this is just to fit with your book. Of the system is, well, actually it's for original system and all the other systems that we got from the original using elementary operations. So my unknowns are x1, x2, x3. So the solution is the vector containing these three expressions for these three variables. So now x3 is free, so let's write x3. x3, cool. x2, well, I have expression 5 plus 3 times x3. There's the expression for x2. And then for x1, the expression is minus 7 minus 5 x3. What can we do? Okay, and we write x3 free variable. It will be important later on. Gorgeous. Because this guy is free variable, it can take any real value. There are infinitely many of those, infinitely many. So for each choice of x3, well, I'll have a different numbers in the vector. So if I choose x3 equals 0, then my solution will be minus 7, 5, 0. Yay. If I choose x3 equal 1, it will be, well, minus 5 minus 7 is minus 12. So it will be minus 12, and then 8 and 1. You're beautiful. But I have infinitely many of those choices. I can take e to power pi, all the things that you can imagine, all real numbers. So that's why there are infinitely many of them. So I'll just write it. the system has infinitely many solutions. And the set of all solutions is given by this expression. Yay. So that's the beauty of it. I'm tempted to do something extra, but I will not. So that's how we do things step by step. So next time, maybe a couple of more examples. But for now, this is how we do it, and you need to start practicing.